face presentation attack detection and defect detection using one-class classification methods. But before that, I will give a very brief overview on unconstrained face recognition and then move on to these two problems, summarize our contributions, and then talk about future possible directions. So I will start very briefly about what is face recognition, what is the state of the art, and what were our contributions in this problem. So the face recognition problem, as the name implies, means assigning an identity to a face image. There have been conventionally major challenges associated to this problem, such as pose, which means the relative angle of the subject with respect to the camera, illumination conditions, when the illumination changes, the automatic methods for recognition or classification of face images, again, a challenge, or the expressions, and so on. So it is basically an instance from a computer vision perspective, an instance of object recognition, which in general, we can consider it as matching a pair of images using smaller components, which we call, or which are referred to as primitives in the literature. So in this sense, we can categorize the general object recognition methods as either bag of words, which divide a bigger image into smaller subcomponents, and then try to find the matching between a pair of images for each of those subcomponents without explicitly taking into account the shape, the general shape of the object, the general structural constraints between those smaller components. As opposed to this first group, which are called bag of words, there is a second group, which is called graph matching. So here, not only we consider an image as smaller components, which we look for correspondences in the second image, but we also require some structural dependencies or constraints to be satisfied. So our work on face recognition fell into this second group because they are more robust to inconsistencies in image capture. So it is a problem which is called graph matching or graph labeling in the literature, which is associated with the probability of a certain configuration, or inversely as the energy of a certain configuration that we would like to minimize. So this is basically the energy function that we had used for matching a pair of images. It had different terms. This first summation measures the similarities between each block in the first image and the second image. So I'm skipping some details so that we can focus on more contemporary problems that we work on. The second term is basically a summation that runs over pairwise nodes, or basically edges of a graph, which enforces two neighboring blocks to be matched into nearby locations in the second image. And if we follow and only use these two first summations, basically we do not have or incorporated any sort of shape of the object that we want to take into account. So we also included another term, this last term, which is a shape prior. It is obtained using face images. It forces the collection of all blocks, which are basically nodes in our graph, to follow a certain shape, basically the shape of a human face. The labels, the unknowns are x's in here. Theta is the parameter that defines our energy function. So it is a computationally expensive problem. What we did was to use what is called a dual decomposition method in the literature. So essentially, given a larger graph, we have divided it into smaller subproblems. As you can see, the edges along with the two end nodes and then try to find the solution to each of those smaller subproblems, and then enforce inconsistency across all of those overlapping subproblems. Because you can, this way, by using this method, divide your problem into a large number of smaller subproblems, then it helps you basically to use parallel processing. So we implemented this method on a GPU at the time, but on top of that, we also use a multi-resolution matching, meaning that we started from a coarse representation of an image, and then iteratively we moved on to smaller and finer representation of the image. So all in all, these two multi-resolution method and parallel processing gave us more than 200 times speed up in image matching. So to give you a sense of what this method can do, in the leftmost column, these are our reference image. Assume this second column from the left as our test images, and our goal is to find one pixel from the left image in the right image that it is most similar to. So we perform this matching in 4 levels, starting from level 3, 8 by 8 blocks, and then iteratively we go finer and finer in resolution until we reach the pixel level resolution. So at the end of the day, for each pixel, we obtain a corresponding pixel in the second image. So one of the widely used data sets for an in-face recognition is called label faces in the wild. It incorporates all of the previously mentioned variations for face images, incorporates more than 13,000 images and more than 5,700 subjects. There are different protocols on this data set. One is called unsupervised in the sense that no labels are provided to any matching method. Another protocol is called image restricted, no outside training data, meaning that we do have access to labels, but we are not allowed to use any data, any image data outside the data set. In addition to these two protocols, although there are other protocols, but we have evaluated our method on these two protocols. So these are basically AUCs, the higher, the better the performance in the unsupervised method, and also in the image restricted method, we obtain the best performance. So if we look into results from more recent methods, basically deep learning methods, you can see that on the same data set, but in different evaluation protocols, deep learning methods achieve more than 98% accuracy. So the point in here is when we are given a limited set of data, then graph matching method, as we followed, is one potential solution because it requires you can perform.
Shervin, can I interrupt? Is it okay that we interrupt, ask questions, or do you prefer to
I will,
get the questions?
yes, yeah, definitely. This is the last slide from the first part, so I will stop here and take questions if there are any.
I'm just curious which deep learning methods you're referring to, the state-of-the-art deep learning methods. These are face recognition deep nets, is that correct?
Yes,
And
true.
what are they?
There are multiple deep learning methods for face recognition. There's not a single one. For example, the VGG face, when it is trained on external data set, it can obtain more than 98%, or even there should be even methods that achieve more than 99%.
I see.
Yeah, there is not a single one. I'm referring to a collection of all of those.
I see.
Yeah.
And this 98 is an average of these collection?
No, it is, you can assume it as roughly the best performance on this specific data set. There can be other data sets that they produce even better results.
I see. Okay, thank you.
So the summary is when we have access to large amounts of data, then deep learning methods can achieve a 98 or, as I just mentioned, even more than 99% accuracy. But when there is limited amount of data, these graph matching methods can be used even using a single sample of the subject. So this is the summary of the first part. If there are any questions, I would be happy to take.
I also have one more question.
Yeah.
So I also worked on face recognition for some time in my past, but we did have these faces, and the cameras are located maybe, more than 500 meters away. And therefore, and these are kind of in the wild. In other words, in the environment is not friendly. We have turbulence, for example. That means there are some pixels already moving, to right, left. So there's a motion blur as well. Just curious that if your approach, because I see that your blocks are kind of, you have these small blocks trying to match with the
Yeah.
original. So you basically introduce this motion yourself to be able to match, to the pose change, to approximate the pose change. And I'm curious that if you, for example, if someone located 1,000 meters away, and because of the turbulence, there is a motion already as inherently into environment. And I'm curious that you don't have that morphology information anymore because it's lost in the image due to the distance. Curious to know, what type of change, or I mean, how would that technique will perform in such circumstances where motion is part of the degradation?
Yeah, thank you very much. That's a very good point that you make. Low resolution images, and on top of that, blurry images are quite a challenge. I have come across a data set. I don't remember the name at the moment, but the data set was collected from a few hundred meters.
Mm,
So, according to my experience, if the image, because when the resolution goes really down, even the humans may not be able to recognize faces. So, if that is the case, below some certain resolutions, I'm not sure that any method would be able to
mm,
provide a very reliable solution. Because if the human cannot recognize from the image itself, I don't know how or how much we should expect learning algorithms to perform. But yeah, I have had other people having challenges on working low resolution images. One
yeah.
possibility that I have heard some people had followed was to use some sort of super resolution methods where they
Mm,
were trying to increase the resolution. But again, that is a learning-based method. And so you have some model that you have trained on some images. Now it is becoming a generative methodology to generate a larger face of some small data. How much accurate is your prediction in super resolution, then directly will affect the recognition performance.
thank you. Thank you very much.
So if there are no other questions, I will move on to the second part. So in certain conditions, when the recognition performance have reached, let's say, an acceptable level, another challenge associated with face recognition image, which is called face presentation attack detection. So there are, let's say, there are a number of people which are enrolled into a system and they are legitimate users. Some intruders may try to access the same system by presenting fake biometric data. So I may, for instance, try to print the face image of a legitimate user provided to the camera to get access to the system. Or if I have a video, I may try to replay it on an iPad, let's say, to get access to the system. Or probably you have seen that there are silicone masks now that resemble to human skin. It is quite difficult even by looking at those masks to tell if it is a mask or the skin of a human. And there are certainly other types of attacks that may have emerged more recently. So this is called face presentation attack detection. It challenges the reliability of such systems. If we consider this as a general configuration of a face recognition system where we capture the data, send it to some component to process the received data, and then another component which we compare the extracted features with those stored in our dataset to make a final decision. We can attack theoretically this system at any point, as you can see, by, let's say, changing the prop, by overriding the decision. But when we refer to the problem as presentation attack, we are focusing on this first component, basically the camera that is capturing the face of the subject. So these are some instances of presentation attacks. Leftmost column, real or genuine samples, and all the others, B, C, D columns are fake samples. So you can see that again, by looking at these images, it is not really possible to tell which one is fake or which one is genuine or bona fide sample, just to illustrate the difficulty of the problem. So the conventional method for this problem is to collect samples from attacks and also real samples, and then try to train a two-class classifier. However, there are certain drawbacks with this method. First of all, you need to set up an environment so that you can mimic those attacks. You would probably need some mask, you would probably need some videos, tablets, and then try to collect all of those fake samples, which is labor intensive. On top of that, the more important fact is that these two classification methods are not very robust against unseen conditions, meaning that if an attacker comes up with a new and innovative method of attacking the system, which is not seen during the training stage, then most probably the whole system would collapse. Our proposition in this case is what is called in the literature one-class classifiers. So we suggested to use a one-class formulation. A one-class classifier is defined as a learning algorithm that can only learn from positive samples. So this is just a simple illustration of two-class versus one-class setting. So here we have genuine samples, attacks, which are known to our system. We train a binary classifier to separate them from each other. Now, if a guy with an innovative idea comes up with an unknown attack, it is possible that that sample would fall on the wrong side of the decision boundary. One-class classification, because it only learns from genuine samples, now it is relatively more robust against both previously seen or unseen samples. So our contribution, this idea has been largely cited and it has been largely followed in the literature, because we have shown that one-class learning is more robust against novel attack types.
And what's the intuition behind it?
The intuition is that when we use known attacks as well as bona fide or real samples, our classifier is relatively more or less biased towards those seen attack types, like, let's say, print attack, replay attack. Now, if a guy comes up with a new idea like mask attacks, that mask attacks has not been incorporated into our training data. So our method would be not be very robust against it. Whereas if we try to learn the essence of genuine samples only, then the decision boundary that we learn would not be biased towards any specific attack type. So all the attacks are relatively more or less in the same position with respect to the decision boundary that we have learned. So relatively more robust than the two-class formulation.
In essence, it works like an outlier detector.
Exactly. Yes, exactly. Okay. So our second contribution for face pad or presentation attack detection was, again, conventionally, people try to train a single classifier which is applicable to all subjects. 10,000, let's say, subjects enrolled into our face recognition system, only a single detection system was trained. So this modeling formalism completely ignores any subject-specific information, the differences or the characteristics of my face with respect to any other user of the system are not explicitly modeled. Our second contribution was to propose to train a separate detector for each subject. So basically, we use the samples for each subject, extracted features, and then using those subject-specific features, we train individualized classifiers, which were eventually, we saw that even the decision threshold for detection from one subject to the other changes. So this method, again, was shown to improve the performance. This table shows a summary of this client-specific versus the client-independent method. These are three of the widely used datasets for face presentation effect detection. These are APCER, BPCER, HDER. These are error rates, so the lower the better. And because we are working with video sequences, we can make decisions based on a single frame or for the whole sequence. So both for the video-based and frame-based scenarios, if you compare these, you can see that the client-specific method sometimes has dramatically reduced the error rate. For instance, this replay attack, we have achieved perfect detection on this data set compared to the case where a single model is trained for the entire data set. Likewise, the same trend is observable for frame-based scenario. So this was the second contribution, our second contribution for FacePan. Third, because in pattern classification, it is well known that ensemble methods are quite useful when instead of a single learner, we use multiple learners and then combine their outputs to come up with a better prediction. We followed this general methodology of ensemble learning and basically classifier fusion. This figure is the illustration of different fixed rule fusion mechanisms. I have taken it from this paper, this seminal paper on combining classifiers. There are different rules for combining classifiers, such as sum rule, max rule, median rule, minimum rule, and so on. But the most widely used is probably the sum rule. The idea is because we expect different classifiers to have more or less independent predictions. Then after normalizing the outputs of the classifier, if we combine the outputs using a simple sum, the output of the fusion is expected to perform better than each single one of those classifiers that are enrolled in the ensemble. So skipping the details, we have used from each face image 8 different regions, extracted 3 different types of features, and then used 3 different one-class classifiers. So in total, 48 classifiers we used. This is a summary of using single best classifier on each of those previously used datasets and the sum rule on all 3 datasets. You can see that the sum rule has reduce the error rate. So here we do not assign any weight to any classifier. We assume that they are equally important and useful for our detection problem. Later on, I will also discuss another method where we try to associate different weights to different classifiers so that the final prediction would improve compared to this simple, let's say, sum fusion. So this is the fusion at the, let's say, classifier level. It is called soft fusion mechanism. It is also possible to fuse, to perform ensemble learning or fuse the outputs of different learners in previous layers, such as feature level fusion. So it is generally believed that the earlier we perform the fusion, the better the performance of the ensemble would be. So we also looked into the case where instead of fusing the outputs of the classifiers, we try to fuse the features. So For this purpose, we propose another method. So in order to go to that fusion mechanism, I will give a very brief review of this method that we introduced. You most probably know that in classification, one of the widely well-known and widely used methods is the Fisher classifier, where we try to minimize the within class scatter and maximize the between class scatter. Here, beta is the Fisher discriminant that we are looking for. So a maximization problem where we are looking for beta. Conventionally, it is proposed for problems of two-class classification, but because we are interested in using only genuine samples, we adapted this classifier into a one-class setting. So the idea is, given some samples, we are looking for a projection such that all of those samples are projected into a single point. If that is the case, then the denominator in here would be 0. So it would, in the limit, be the maximum value that we can achieve for this Fisher ratio. Then what is the sample from the second class? We assume a hypothetical sample from a second class, the origin in that one-dimensional subspace. This is assumed to be the single outlier or negative sample. So if we can manage to do this, then any test sample, when projected onto the same subspace, we will measure its distance to the projection of our samples, basically target distribution, and that would give us a score how much genuine or how much fake our sample is. So this is possible, but again, this minimization problem or maximization problem would require matrix inverses, eigendecompositions, which are not always very easy to compute. On top of that, basically computationally expensive. On top of that, it is basically not regularized. So if I project all of these samples onto a single point, I'm basically overfitting my model onto the target distribution. They're all projected into a single point. So instead of solving this, we propose this relation regularized regression problem. So I will start with the second sum. These are theta are the unknown parameters of our model that define the projection. We assume that all samples are more or less to be projected around point 1. You can assume any non-zero point in here. And then Vxi, xi is our input feature. Vxi is the projection of that feature into the kernel space. So what is the regularization? In order to avoid overfitting, we introduce another regularization in here. It is typically called in the literature Tikhonov regularization. And then this whole some optimization problem in the kernel space, instead of directly solving it, people usually use a dual formulation. Skipping the intermediate computations, this is the relation that we're interested in. We are looking for some omega, the discriminant in the kernel space. Everything regarding our training data in here is captured in this single K, our so-called kernel matrix. It encodes the similarities between our training data. This maximization is quite easy. You take the derivative with respect to omega and then set it to 0 to find the solution. So this K, for a single feature, we will have a single K. Now, returning back to our feature fusion, we considered multiple regions of the face image, the entire face, different parts. And for each of those regions, we extracted features using pre-trained models like GoogleNet, ResNet, VGG16. Then we came up with 12 different representations. For each of those representations, we constructed one of those so-called kernel matrices and then fused them using a sum rule. So this is a common approach in kernel methods, the sum rule over the kernels. When you do this, you're effectively fusing the features. So this is a summary of applying this method on 4 different data sets: replay attack, MFST, Ulu NPU, and replay mobile. At the top row, we have AUCs, so the higher, the better the performance. Bottom row, these are different types of error, the lower, the better. So on 2 of the 4 data sets, we achieve perfect performance. On the remaining 2, we achieve, again, the leading performance compared to some other methods.
Shervin, can I have a question?
Definitely.
Can you go back 2 slides? So it's a convex optimization problem, right? So
Yes.
and the one that you find as dual is quadratic optimization. So I think it makes it even easier to solve.
Yeah.
Curious that, if you look at Fisher's optimization, we can find a closed form expression for that, right? Is that correct?
Yes.
But you're saying finding eigenvalues and eigenanalysis in general is harder because of the matrix sizes?
Yes. And on top of that, because it is not easy to incorporate regularization in here.
In here, yes, I
So
see.
yeah, at the end of the day, we will end up with a very perfect projection, projecting
Yeah,
all
yeah, yeah.
samples onto a single point. So kind of overfitting.
Okay, curious that, so when you come up with this, regularized version, is the results are going to be the same? I mean, in terms of
Now,
from,
yeah, very good question. In terms of the projection, when we incorporate regularization, not all the points will be projected in here. We will have
right,
a distribution around this
I see.
point, which is the peak of that distribution would most likely be this point, but we will have also samples at the 2 sides, left-hand side of this center point.
Okay, so your novelty score is going to be the distance between the test sample and the closest sample that can be driven from that distribution, or is it
That
like the mean
the first option is also applicable, but we use the distance from the mean.
from the mean? I see. Okay, I see.
Because
So,
in practice, if we measure the distance from a test sample to the closest positive sample, then
mhm,
positive samples or positive training data sometimes may include some sort of noisy data.
right.
Or data may not be perfect. So it is
Mm,
possible that some
mm.
of the samples may lie where they shouldn't lie.
I
So
see, I see,
that's
I see.
why we measure the distance again to the mean, to the
I
center
see.
of positive sample.
I see, I see, I see. Okay. All right, thank you.
Thanks. So our last contribution regarding phase path, this is again the same relation that we just saw. Our kernel matrix, we replaced this in our previous contribution with multiple kernels. We use a sum of different kernels. We assumed equal weight for all of them. But that this fusion completely ignores any discriminative advantage of each of these features or kernels with respect to the other. It is likely that some features may be more discriminative, more useful for our problem, others less useful. So we extend that idea to this second method where we assumed a weight for each of those kernels. So the weight, we expect a weight for more useful kernels to be larger, for less useful ones to be smaller. Then we also assume that all those
Mm,
weights should be non-negative, and
mhm.
then we are free to impose any sort of other regularizations, other assumptions that we would like on those weights. This is in the literature, this is a well-known problem which is called multiple kernel learning. So in the multiple kernel learning problem, it is common practice to impose some sort of sparsity on the beta vector, meaning that some of the elements would be shrink towards zero, some of them be larger. There are different possibilities for enforcing sparsity. We consider 2 of them. One, LP norm. and then the other matrix RP norm. Both of these regularizations for this prior assumption on the weights impose sparseness, but the second one is basically a more generalized form of the vector LP norm. So basically, if we set R and P equal to each other, this matrix norm would be simplified to the LP norm. So the second one is a more generalized version of the vector norm. Again, skipping the intermediate computations, we show that both of these optimization problems for vector norm or matrix norm regularization are convex. We propose analytical solutions and then solve both of these methods in order to give a visual idea what the vector norm or P for the vector norm would do. This is the smallest p-value that we consider equal to 1. Smaller than 1, if we consider it would be a non-convex problem. So we consider a smaller value equal to 1 up to any larger value that we would like. The smallest one gives us a very sparse vector. This is the value of the elements of our weight vector. As we increase p-value towards larger and larger values, for instance, 64, you can see that we have obtained an almost uniform weight vector, which is very close to sum fusion rule. So by playing with that parameter, we can control the weights that we assign to different features or basically to different kernels. We evaluated both of these methods on the Udo MPU facepath dataset. This is again the error, so lower the better. These are our methods, the vector norm and the matrix norm. Both of our methods perform better than the others, but as expected, this matrix norm even performs better than that vector norm. So that is the end of the second part. I would be happy to take any questions if there are.
I have one, if I
Yes.
may. So there was a slide which presented like four cropped versions of the same person, right? Yeah, okay. So is resizing, cropping the only data augmentation method that you have utilized during training?
Yes,
Yes.
we first crop these, but as these most of CNN, pre-trained CNNs, because they need inputs to be of a
Same
certain
dimension.
size, we resize these regions to match the input of any CNN that we would use.
Yeah, they have to be the same dimension, but the part I'm curious about is you did not apply different augmentation methods because you don't want the representation space to be similar to perturbed or adversarial samples, right? Or is it something else?
Uh, We use, first of all, we use genuine samples, or let's say real samples. Then we try to extract as much information or as much different information as possible at the time from those genuine samples, both in terms of different regions and also in terms of different features. Definitely, there are other regions that you may consider, and they even may help to improve the performance. And also there are definitely other deep pre-trained CNNs that you may consider and other transformations, other geometric transformations, probably, I don't know, even rotating these or even scaling these slightly would probably help. So our main objective in here was to show that a kernel fusion is helpful in improving the performance. So data augmentation can take different forms, as you mentioned, but we have not explored all possibilities. We have just limited our attention to a limited set of features to show the validity of fusion.
Okay, got it. Thank you.
Thanks.
Shervin, I have a related question. I don't want to be the stopper. I know we have limited time and you have limited time, but just curious that you said that fusion, earlier fusion, is more beneficial than.
Yeah, that is a general belief in the sense that we have our data, we have our feature, then we have our soft prediction probably by the classifier, and then we have our hard prediction. The classifier tells this class, not all the other class. So the general belief is that during this spectrum of the data to the hard decision at the final stage, the earlier we perform the fusion, the better the fusion or the more helpful the fusion would be.
But so you're saying that doesn't depend on how we fuse, however we fuse, it's always beneficial, or the general belief is that it's always beneficial to fuse earlier than later. Did I get it?
It is a very general idea. Apparently, if we follow a not very effective fusion mechanism, even at the data level, then we would not achieve very much improvement in the final performance. The assumption is that we have access to effective fusion mechanisms at different levels. If that is the case, the general belief is go for the earlier fusion that you can fuse.
Got you. All right, thank you.
Thanks. The last part, with the advent of these generative methods, you have probably seen deepfake images, or even video sequences that look very realistic, but they are in fact not real videos or images. This is an illustration. This is the real image. Although I'm going over images, it is also applicable to videos. Here, the expression of the subject is changed, so it is called manipulation, or in general, deepfake. Here, the expression remains the same, but the identity of the subject has changed. Here, the attribute, the color or form of the hair, and also the glasses have been added to the subject. So again, some sort of manipulation. Hey, here we have a completely fake subject. So it is quite important to be able to tell if an image or a video sequence is fake or not. Conventional face recognition system, if you provide, for instance, this image to the system, it will not be able to detect whether it is real, it is manipulated or not. So quite important to detect any type of manipulation. And this last part of our research focuses on detecting whether it is real or manipulated. So this is an illustration, a very short video that I would like to share with you. Okay, so these all 6 different videos, just by looking at them, you can see that it's not really possible to tell which one is real or which one is fake. So again, quite a difficult problem. This is what we would like to tell. We are not looking for a type of manipulation. We are just trying to tell if this video is fake or this image is fake or not. So this one and this one was real. All the others were fake. So back to...
Do you know humans' performance? I don't know if you run such experiments, but maybe some other
Very
groups
good
actually.
question. I'm not aware of the human performances, but to be honest, I don't expect a very high performance even from humans. So because these videos, I have obtained these videos probably a year ago. You know better than a new, more powerful generative method is developed every day. So the quality is even better than this.
Right.
So our idea here, again, followed a one-class classification approach. We assume the real samples to be positive samples, any fake samples to be outliers, negative samples, and then try to train one-class classifiers. So a very well-known method for one-class classification, it's called support vector data description, a one-class variant of the SVM or support vector machine. This is the idea. Given a collection of positive samples, the method is trying to enclose them in a circle or a hypersphere in a higher dimensional space, such that the radius is minimum. So the hypersphere should be as tight as possible. The number of samples or negative samples that are inside the hypersphere should be as small as possible. The number of positive samples outside that hypersphere should be as small as possible. So this is the relation or the optimization problem that they have suggested. R is the radius. These two summations are the summations over these errors. One over positive samples, the other over negative samples. So tightest hypersphere with minimum sum of errors, but it has two constraints, forcing positive samples to fall inside the hypersphere and negative samples to fall outside the hypersphere. So this is a very well-known method, de facto a standard in one-class classification. We started with this method and extended this. You can see that the errors in here in this relation are linearly penalized. We suggested generalizing these errors by using a power of p bigger than 1. That is helping us to nonlinearly penalize error. That is one contribution. Then we introduce another term to enforce a large margin. So visually, what we are trying to do, given this solid circle as the original decision boundary, our method force positive samples to be enclosed in a smaller circle, that is the large margin concept, then negative samples to lie outside another bigger circle or hypersphere in a higher dimensional space. And then any errors, you can see that these are the errors, instead of naively penalizing them using a linear penalty, we introduce a power of p so that we can control the nonlinear penalization of each of those errors. So these red terms were added. The dual is common practice to solve the dual. The dual, I have written it in here because the dual is also interesting to look into. Beta is our variable that we are looking for, the unknown. Because of these Q norms, by playing with P and Q, which is the dual norm of P, we can control the sparsity of these betas. So in the SVM method, we do not have a direct control over the sparsity of the discriminant. But here, because we introduced that free parameter, it appeared in the dual space as a dual norm, which we can play with to control how uniform vector B is or how sparse it is. We introduced an optimization method for this, solved it, and then we also studied this large margin method using Rademacher complexities to show both theoretically it improves the performance as well as by examining it on datasets. Before presenting the results of this method, our last contribution is on classifier fusion. So this is that sum fusion. In the simplest sum fusion, we assume WIs, the weights that we assign to each of those FIs, classifiers, are equal. We thought that, as I said previously, some of those classifiers might be more useful for our task, so they should receive higher weights. So we designed an optimization algorithm to learn those weights. What is the optimization algorithm that we designed? It is based on a hinge loss for people working with SVMs. This is a well-known loss function referred to as the hinge loss, but we incorporated another prior on those weights. So by solving this and playing with that p parameter, we could control either we give a very large weight to a single parameter classifier or distribute them more evenly between different classifiers. So the p parameter is a key parameter in fusing different classifiers. If you are wondering how we set p parameter, it is set in using validation data. So we find the P that maximizes the performance on our validation set. So a few insights about this fusion. By taking in the limit P to the infinity, all classifiers receive uniform weights. So it simplifies to the sum fusion rule by setting or in the limit setting P to 1, we will choose the single most confident classifier in the sense of maximum average margin. You can think of this as the single best classifier. If we set P equal to 2, then we will recover the ordinary soft margin linear SVM. And then you can see that by playing with P from 1 to infinity, we can sweep the entire spectrum, which we can use to fuse our classifier in the problem. So summary of these two results, Face Forensics++ dataset is a very widely used dataset for deepfake detection. It has 4 types of deepfake videos. These are DF, FF, FS, and NT. These refer to each one of those types of deepfake videos. There are 2 versions of the dataset that are commonly used. One is relatively higher quality. It is called C23. The other one is much lower quality. It is called C4. So we tested our method, and both of these 2 different versions of quality reported the performance in terms of AUC. Again, the higher the number, the better the performance. I have summarized some of other best performing methods. The point in here is that if you refer to the literature, you can see that there are some methods that report 100% performance for all types of these fake samples or subsets of our data set. The point in here is that we evaluate our method in a leave one type out scenario, meaning that at each stage, we use 3 types of these deepfake videos for training and then 1 type for testing. So this will mimic the realistic situations where you train your model, someone else comes up with a new generative model, and we would like to realistically measure the performance of our method on unseen new models. So again, both of our methods achieve very good performance, but the large margin method performs slightly better compared to this classifier fusion, specifically on low quality samples. So that is the end of the third part. I have only 3 more slides about possible future direction. So if there are any
Please
questions.
go ahead. Yeah, please go ahead.
Okay, I will quickly move. In terms of classifier fusion, we can assign different ways to different classifiers based on which local region of the feature space those classifiers are. So locally adaptive weighting is one possibility. And also we didn't theoretically study the fusion compared to single classifier. That's another possibility. In terms of kernel methods and deep learning methods, we had previously worked with one of my students in fusing kernel methods with deep CNN learning, but we think that because kernel methods offer very sound mathematical basis, it is advantageous to further investigate how those 2 methods can be fused for better performance. And finally, because we are working with streaming data, basically video sequences, in all of the previous tables that you saw, we inferred a single prediction for a single frame, and then average all the predictions for all frames to come up with a single decision for our video sequence. But we think there should be better alternatives to fuse predictions over single frames. So the generalization of our methods to sequential data streams is another possibility. Okay, thank you very much.